Hi, welcome to our latest talk. We hadn't a talk for quite some time now. This is the first time we are recording a talk. Yes, perfect. I will say this talk is a special recording for me because it works on Linux completely. Cool. So, welcome to Zürichsee. Thank you very much to Leap for having us. The slides will be posted here on the GitHub repository. I'm not sure if we will upload the video as well to this location, but Git can handle gigabyte files. So we have two upcoming events that are already fixed. First of all, we have RustFest EU conference. The latest news from my team members is that we are going to sell the first batch of tickets later tonight or tomorrow. So if you have Twitter, follow us there or use some other tracking device of your choosing and follow our blog. It will be at ETH Zurich, so nearby. The other thing is we have a September meetup, beginning of September at Cordamp, which is in Rapperswil. It's 35 train minutes from the main station, so easily accessible. To our main topics, admin, Fratpool, and cargo helpers. We will see if we get to the cargo helpers, if we have time. If you have questions, just shout in. We can also try this with the fancy microphone. And yeah, so admin stuff. We made a Verein. Woo! 10th of July, we founded a new entity for Rust-related stuff in Zurich. So it's called Zürichsee, because we have a lake. We're currently looking for our more locations, and if we find a company paying a pizza bill or something like that, we could also offer food at the meetup. So if you know somebody, please find us. Locations would be really nice. Cool. Told about the tickets, yes. So, let's go into the Fratpool. The Rust Fratpool is the oldest Fratpool crate that we have. Oh, I forgot to ask. Who has done something with Rust? Please raise your hand. Everybody. Perfect. Almost. Okay, so the Rust lingo. A crate is a module that's separate. We have modules within crates to structure our code, but a crate is an external thing that you take in as a whole and can reuse it. It's way cleaner than the includes from C or C++. And yeah, Cargo, the build manager, can build everything in parallel. It builds a dependency graph and generates your opcode. The Fratpool crate creates the worker threads eagerly, which means when you create it and tell it I would like to have 20 workers, he spawns 20 threads and then waits. We have a job queue which uses a mutex. The reason for that is this crate builds completely onto the standard library, with one exception, which I'm going to talk about later. But all the core functionality is from the standard library, so we don't have any fancy work-stealing queues. We have the standard channel, which requires one mutex. It's usually not that big of a problem. The pool is now joinable, like a thread, so you can tell the pool, hey, join on this, return when everything is done. That's the function I made, that's why it has a smiley. We have a really fancy documentation system. Every crate that is published will be fetched by the docs.rs system and then build the documentation for you. So we have every thing that builds in a Docker container, which means the AMD 64 architecture or x86 64 if you prefer Intel speak. Everything that builds on that platform will have its docs available with the scheme docs.rs/crate name. And when you open this URL, you will be redirected to the latest version. You can have many versions of the documentation, compare stuff, and it's quite handy. So, let's start with a channel. Channel is the magical queue I told you about before. So the job queue is just a channel. In Rust, we can write it like this. We have a channel returning a tuple with a sending and a receiving end. We can move the receiving end of the channel all over the place, move it to different threads, and we can copy or clone the sending end of the channel. So this is a multi-producer, single consumer channel. If we use another channel for our artifacts, so the stuff that our pool will calculate, we can use the channel to work as a pipe, because we drop jobs into the pool, it starts working, and after we finish dropping jobs into the pool, we can start consuming every result the worker threads produced, while more results get produced. The only problem with that is if we have too small messages, we can flood our system. This problem arises when you have NUMA systems. So this laptop is technically a NUMA system. It has only one NUMA group. The NUMA is the non-uniform memory access model, which allows to have more cores on one physical machine. And as soon as you start jumping from one group to another, you get performance penalty. So when you have a big server system, like 64 cores or more, this starts to matter. On the laptop, you don't care. It also allows you to group tasks. If you have many jobs, you can use, I don't know, 4 or 5 channels. For each group, one channel, and then start consuming partial results from each of the channels. A con is because if you use iter, it means turn the receiving end into an iterator and iterate over everything that comes in. You must drop the initial sender because the iterator will wait for all senders to go out of scope. If you don't do that, you hang at some point when everything is done. It's quite a stupid bug. So let's look at the code. If you can't read it, come closer. Basically, we have this line here. We use stuff. So we use the Fratpool from the library, and we use the channel. Then we create 4 workers and 8 jobs. Create the pool. Sorry, this is just how much. This let is the declaration of let something named here and infer the type. After that, we actually create the pool. At this point, the worker threads are created and they are waiting. Since the receiving end of the job is in a mutex, the first one will get the lock and wait, and the others will wait for the lock. Quite simple. After that, we have a for loop, and we spawn everything. So at this point, we create the channel. Here we clone the sender, and then we move the sender into it. I'm not sure if you can see that from back there, but this says move, double pipe, and then a block, which is the syntax for a closure, or a lambda. Double pipe means no arguments for the closure. And the move statement here says everything that's referenced in here that comes from out there will be moved inside, which technically means copy and then don't access it outside. So we create a sender copy for the channel, for each thread and immediately send a 1, just a number 1. And then after the loop, here we drop the initial sender. We can explicitly say there's this function called drop. We can say free this memory here at this point. So at this point, when the pool starts spinning its thread, we have reduced the amount of senders, and this over here is a assert macro. Come back to that later, where we take the receiving end from all our from a channel, iterate over all results, and fold them. This fold starts with 0 and basically is a sum function. And sum works with numbers because it's a addable type. Yes, so what I didn't mention is the assert macro. Macros in Rust are hygienic, which means you don't have this copy-paste stuff from C. You have AST manipulation. So you don't get double execution or other weird stuff within a macro. It's just as if you wrote different code there that the compiler does. Yeah, so questions so far? Yes.
Could it happen that the execute is so fast that iteration wouldn't catch it?
No, well, maybe. So if we had, I don't know, a single core system which would, for some reason, execute all the jobs in the pool first, the results would not get lost because the channel would just buffer them. So this is an unbuffered channel here. We can also have a buffered channel which has then a fixed buffer size. We can set that to 0, so it will block, or 1, just one element. But yeah, sure, if the operating system decides to do funny stuff, it can. Won't hurt us. That look. You may correct me if I'm telling wrong stuff.
I'm just not sure what funny stuff could happen.
Well, the operating system could decide that your main thread gets lower priority for some reason and just not schedule it until all the work is done.
But you would still get all the results, they would not be lost.
Yes, absolutely. And it wouldn't change the outcome. Maybe the runtime, but not the outcome. So, another way to synchronize stuff is using a barrier. If we stuck a barrier inside an arc, we can do synchronization. An arc first, or first a barrier. A barrier is something you call n times, and it will block until the nth time and then reset. So we can use that for, I don't know, if you have a barrier with a thread count of 4, 4 threads can call the barrier more or less simultaneously, and as soon as the last one hits, all of them go. So that's the synchronization mechanism of a barrier. So to distribute the barrier into all threads safely, we have to use an arc. Arc means atomic reference counting. Since we don't have any garbage collection in Rust, we have to make sure we don't lose memory on the way. And we use reference counting, and multi-threaded reference counting requires atomic operations. So we have an arc. You see here, the arc is constructed with the whole barrier inside it, which means the arc owns the data. And since the arc can take care of how many copies to the arc, how many references, are around, it knows when to deallocate it. And after we have it, just store it. The arc has the fantastic clone function, which allows us to copy the reference, and then we move it into a closure. Pro, we can also group tasks. Con, it's really easy to deadlock with this kind of synchronization. And the reason is this assertion must hold true at all time. Oh, I forgot to change the font. I'm not sure if you have noticed that this is the math style of this equation. It's a really Fira code, is it called. It takes some combinations of symbols, for instance equal and more than, and merges them together to form a nice symbol. Makes your code look pretty and very confusing to strangers. So in the case of a barrier, we must make sure that we don't have more jobs waiting on a barrier than we have worker threads running simultaneously. Yes?
But then if I understand this right, doesn't that mean that the assertion actually has to be that the number of jobs is a multiple of the number of workers?
Wait, you ask if the number of jobs must be multiple of the number of workers?
Or wait, maybe the other way around.
Yeah.
But
No, we can fill up to the point where we have exactly as many threads running as we wait for. It's capped. If your pool has just one job, task, whatever, to do, one incentive to solve, then you can go to the maximum of the pool size. But usually this will lead to the situation where you have a pool with 5,000 workers executing 5,000 jobs at the same time, which will kill your machine. So that's not an option. But as soon as you have 5,001 jobs in the pool but only 5,000 workers, it will deadlock. Because the threads are waiting for the last thread to also wait on the barrier, but it will never get scheduled. So it will never be able to reach the barrier. So your system will just halt and deadlock. Yes?
John, all this synchronization things we talk about is just to wait for all threads in the thread pool to finish their job.
Yes.
That's okay.
Yes. So it is just how to coordinate workload that you drop off into a thread pool. Maybe it's clear when I show you the example. It's getting messy. Sorry. So we create pool and something atomic. This is an atomic. It could also be something outside of the system, maybe a network connection or a file or whatever. Then we also have this assertion, which must hold true, or we will deadlock. Here we create the barrier, and since we want to wait for all our jobs plus our own thread, so we know whenever this barrier passes, we have the result that we are waiting for. So that's why there's a +1. And then the same as before, clone references to the barrier and the shared state that we would like to change. And then execute in the pool. And here we do all the heavy work. In this case, add 1. And then wait for the other threads. Here we wait also. So this whole messy scheme is just for one thing. We would like to wait here until the whole pool has finished. And that's really messy. And the only two options you had before was either do that or use a channel and know exactly how many results you will receive. But the problem there would be if something panics, you have to prepare for that. Lots of other crazy stuff.
But if something panics here before waiting, you have the same situation.
Yes, that's a problem.
Also, I'd like to point out that for me it was particularly confusing when I worked Rust, that you define the barrier like that, and then you can call barrier.clone, which is on the arc, but also barrier.wait, which is on the...
Oh yes, oh yes. Yeah, it seems confusing why this, the arc does not have a wait method, true, but we have auto dereferencing in Rust, which is really nice. And
And confusing.
yeah, a little bit confusing. You get used to it. You can do lots of fancy stuff with deref traits and mut deref. The main rule for me here is just if the compiler tries to find something on the thing that's derefable, that's not there, it will deref it at least once and try to find it. Yes?
But I think, in my experience, yeah, you get used to it. You start to think about some of these things like arc and RC and things like that, kind of like pointers, and you don't really, they become mostly transparent. You don't even see them anymore, so to speak.
Absolutely.
So any of these types that exist to hold something else or hold a quote unquote reference to something.
Yeah. Yeah, same with the mutex. It also just encapsulates some data that you would have to deref to access. So this was the situation for quite some time, and lots of people complained, and everybody was just like, ah. So I made a join operation. So you can submit new jobs to the pool while you're waiting. Just I did not plan for that feature, but it just resulted in the design, just like, oh, fancy. Also, many threads can wait for a pool, which is also fancy, but not intended originally. There is one thing, since I allow many threads to join on a pool, there is a possibility to deadlock yourself, which after careful consideration would also mean you could deadlock on yourself. Ta-da! I'm sorry. That's how it is. Never join your own pool. You will deadlock instantly. So, here we have an example. The same as before. We have a pool, we have some jobs for it, and we join. Easy. No more barriers, no more channels. Just if I have a pool that's working files which don't overlap, like a thumbnail generator, I just run it and join the pool afterwards and be done. It's the easiest solution for stuff I don't care about the return value inside the program, because the effect the program is having is outside of the program. It's really handy. A little more complicated example. We have one new use here. So we know the Fratpool and we have the arc. Now we have the atomic use size and ordering. Ordering, for you, if you don't know it, it's how relaxed or how strict the memory access model for atomic stuff is. So in our case, we have it very relaxed, which just means I don't care exactly how or when my atomic write appears, but it must be correct. So there are stricter ways, like release or acquire, where I say if I want to write or read something, the events must be visible before or after, or sequential consistent, when I don't allow any reordering of the instructions. In this example, reordering is not much of a deal because we only have one instruction. But when you have a large program and build lots of stuff and many threads are accessing many things at the same time and maybe wait for one thing or another, there comes a time where ordering is really, really important, because the compiler can decide to reorder your instructions if they are independent enough to do so. If you ever run into multi-threaded problems in C or C++ or Java, think of ordering. Ordering might kill you. Or C#. C# has also very lax ordering per default. So, example, we create a pool, create globally shared state, safely shared state, spawn 42 threads, copy the reference, the counted arc over, move it into each thread and add one. After we join, we have the result ready. Yeah, that's basically it. Any questions?
They will use the Threadpool? Like, can you do this several times?
Yes, you can join multiple times.
So join basically just means the thread pool is currently empty? Or
Yes. No more jobs in the queue, no more jobs running.
But you said you could join from multiple threads?
Yes.
You also like add new jobs from multiple threads?
Yes.
Because then it would get racy again, probably.
No,
Join it and then another thread pushes a job on it and you think it's finished, but there's...
well, there is something called the conditional variable in the background, which I will show you later. So if we have many threads adding jobs and joining on stuff, we don't get a race condition at all. I have a test written for that. It's really nasty one. 2 pools giving each other jobs and joining on each other, and it works. So, yes. Let's go over this. I think I have the code later in the slides, or if I don't, I can just go over to the docs and read, or the source code. So if you want to have more examples, in the Rust cookbook is an example for not Mandelbrot, Julia, calculating the Julia set with Fratpool. They spawn, I don't know, some million jobs onto the pool and calculate stuff. It's really fast. Maybe it would be even faster if they grouped, I don't know, segments of 100 jobs within each, 100 pixels within each job. So, since you don't have any questions, let's go on to the architecture of the pool. I already hinted it. So, this is the complete code for the structure. This is all the fields that are in the Fratpool. We have a sender, which will be clonable, and we have a reference to the shared data. For those of you who are new, we have this derive up here. Derive means, dear compiler, I'm too lazy to write boilerplate code. Just implement a copy operation. And the compiler will complain if you can't do it. There are also other implementations like debug or other fancy stuff, equal. If they're easy enough for a type to just be auto-generated, you can just tell it with derive, do stuff. So,
So does it mean to clone a Threadpool? You will still have the pending jobs on the copy also?
yes, so clone in general means allocate new memory which either has the same meaning or in this case points to the same data. And in this case we clone the sender and the shared data, which means when you clone a pool you get a new entry point for submitting jobs or joining onto the pool or changing the amount of worker threads.
Okay. In other words, you don't need to wrap an arc.
Yes, you don't need to wrap an arc around the Fratpool, you just clone it. Also, if you did use an arc has the limitation that the stuff it takes is not mutable anymore. And you cannot change the stuff if you don't have a mutable reference. So an arc would not be handy in this case. Shared data is rather simple. For now, let's focus on these 3. We have the receiving end. We only have one receiving end per channel. That's why it's inside in a mutex. We have this empty trigger and the conditional variable, which are required for the join operation. And we have some bookkeeping stuff for the queues and a name. This name is actually quite handy. You can do that in other languages too. You can name your threads. So when they crash, it's not just crashed thread number, I don't know, 157, which is useless basically. Can name them, can tell it, this is a pool for fetching stuff or calculating thumbnails or whatever. And then when one of them crashes, it tells you, hey, one of these threads crashed. Can do that with any thread. You can create a name for every thread if you like. And just, yeah, this is my bubblegum thread, and this is my water thread. Really handy if you have many of them. Oh, by the way, do you know what this means here inside the bigger and smaller? This. Bracket open, bracket closed?
Empty type.
Empty type, yes. It's the unit type or empty tuple. The reason for that is usually the mutex in Rust takes data inside it and guards it against misuse. But we just use it as a trigger. So there's no need for any data. So just use that away. And the compiler will optimize all the safekeeping for actual data away. So it will just reduce it to the actual mutex, like you would write in C. Cool. So, if the Fratpool is out of work, it will notify the other threads. Maybe you should change the slides of that. So after every job that's finished, the worker thread will check, is it still needed? And was I the last one doing some work? This is the function that's implemented on the shared data. So, yeah. And if we have no work, we acquire a lock for the trigger and then notify all the listener. This is, I think it's called observer pattern in Java. Yeah, this is that. This is the notifying end. On the other end, we have the join. It has two whiles. I'm not sure actually if the outer while is necessary. I haven't found the time to investigate that. Basically, it's just a safeguard to, is there really no more work? And then try to acquire the lock, check again if there's no more work. And now we have the condition variable, which says you take in here, you take in the lock, which is really important if you have seen Rust code. Usually you have an ampersand before you pass in stuff that you get out. But in this case, we actually want to give the lock away, because when we do that, the lock can be unlocked. So when it enters the wait function, the mutex will be free, because otherwise the other thread, which will try to lock it, this will never return if we don't unlock the mutex first. So at this point, when we are waiting, we give the lock away and wait. This will wait for quite some time. Sometimes it wakes up for no reason. That's the reason for this while. So we have to check again. Sorry. But as soon as the wait returns, we get the lock back. It's the same lock, but it's just syntactically covered that we don't lose it anymore. Yes, and I'm really starting to think the outer while is wasted. Yeah. Always great to give a talk. You learn so much about your own code. Cool. Oh yeah, here you see reference, just ampersand, which means it's a borrow to self. Self is this from other languages. Just explicit in Rust that you always see it and always know which one is your this. Cool. Questions?
How is work implemented? Is it using some Mutex instead or Tommy counter?
Pardon, what's implemented?
Shared data dot as work.
Shared data. This one. Mm-hmm.
And he has work function with it acquires a lock on job receiver.
Oh, you mean for the notify?
Yes.
Yes. So first it checks itself has work false. I don't like this. I actually prefer it to if self housework equals false. If there is no more work to do, it will try to acquire the lock. That's very
Yeah, but
prevent
the
the-
function Housework, is it, it acquires a lock inside it, right?
No, the housework basically works on all these, no, just on these two. It fetches the queue count and active count atomically and just adds them and sees if it's still 0. No, don't add it. I think it just fetch the first one compared to 0, fetch the other one compared to 0. That's
Shouldn't it actually be that way, that you fetch both of them at the same time?
You
You cannot do it automatically with both. Doesn't really matter. It's always 2 steps to fetch 2 distinct atomic states.
Okay, but couldn't it be that something gets pushed onto the queue while you're checking the second one? While you're retrieving the second one, rather?
Well, sure, in theory it could, but it's highly unlikely. It's prevented. I prevented it like this. When you submit a new job, before you enter it into the queue, you increase this atomic queued counter by 1. So there is a state where, for a really short amount of time, there is one job accounted for that's not submitted, and then it takes time for the queue to for the channel, which is the queue. This receiver. It's not instant. It has also many operations. So you start execute function, give it the reference to your function, increase the counter, and then hand over the reference to the function into the channel, which takes time. And then when all of this goes through, at the other end there is a mutex to be locked. Maybe it's already done. Let's consider it's already done. So the second thread has the mutex, gets the reference to the function out of it, then has to free the mutex, unlock it, and then start the accounting, bookkeeping, add 1 new job processing, remove 1 job queued, and then actually start working on it. Even if it's a no-op, it has to deref the function, which takes more time than fetching 2 atomics. And then after that it has to do more bookkeeping, and then it has to decrease the atomic active count, and after that do some more bookkeeping about is it still needed or not. So I think yes, in theory, but highly, highly unlikely. We could look at the code, and I changed all the load and store operations to sequential consistent, so I don't have reordering issues at some point. Because when the compiler thinks, yeah, I can reorder that stuff, then it gets messy. So I'm pretty sure sometimes, for short amounts of time, there is 1 or 2 jobs too many.
So you are sequential, and you're saying you're increasing the active count before decreasing the queued count, right?
Yes. And I think that's why it may be overaccounted for the jobs.
But never
Something.
undercounted.
Never undercounted. And this should prevent that. And even if the rare condition would be, let's imagine if the pool is empty, and then you join on it and test for all the stuff. It could be that somebody else, while you're testing, is starting to insert a new job. But then is it wrong to look at the join as completed, because you will return from the join with the first thread while the other one is still trying to insert a new job. So it's racy, yes. Is it wrong? Yeah, depends. And if you have that kind of a problem, you could also just use more synchronization. But I think it's sound so far. So, yes. Yes, please.
On the other slide, there was a check for execute as empty, and then signal the variable.
You mean this one?
The ASCII. Yeah. So
Mm-hmm.
what happens if there's no more work,
Mm-hmm.
and then before it triggers, somebody submits new work?
Too bad. If you insert at this point a new job into the queue, you miss the window. It's too late. It's very it's racy. Yes, it's not unsafe. So this happens.
So it will set off all the joins at that point.
Sure, but triggering the empty event and handling the condition variable will take time. Plus, these guys will have to acquire the lock again, because until they don't have the lock, this function will not return. So they have the mutex again when they have the lock here in this symbol. And then the while function starts over, checks if there is more work. If the work has already been submitted at that point, they will just join again. Just wait for another round. So that case where inserting here should not be a problem. Could be, of course, in theory, but highly unlikely. Okay.
It happens that only one, like if you have several threads waiting on join.
Oh wait. Let's try this one. Woohoo! I really wanted to try this one out. So I feel like a pro.
Can it happen that?
It works. It works.
Can it happen that if you have multiple threads joining,
Mm-hmm.
only one of them gets out if you essentially have visitation where another thread inserts something at the same time in queue in the pool?
So many threads wait already.
Yeah, you have
And-
like let's say two threads waiting on join,
Mm-hmm.
and the pool is empty,
Mm-hmm.
and they get. So now we're trying to. We got notified. We are trying to get
Mhm.
the lock.
Mm-hmm.
The first one gets the lock,
Mhm.
goes out of a join,
Yes.
and before the second manages to get the lock,
Mm-hmm.
another thread inserts something in the queue,
Yeah,
and
it's possible.
the second thread gets still waiting.
Yeah, I imagine if you have 1,000 threads joining on something, and while the first one is getting out, it starts inserting new stuff. I'm pretty sure that would happen. Yes. It's a limitation of the physical world, I guess. As I don't see right now a way to prevent this behavior. But yeah, this would probably lead to a wave of threads correctly leaving the join and another part not leaving. Yeah. Cool. More questions? So, I think we have 40 minutes now of talk time. Are you still ready and shaky? Should we do the next part? Cargo helpers? Yes. Okay. So, cargo helpers are cool. So, my favorite is cargo outdated. It's the first cargo extension I ever installed, because at some point it was in the early development of Hyper, where it's just like, it's broken, why? And then instead of just randomly update, which would break stuff even more, you could just ask cargo outdated what's outdated, and then explicitly tell this crate to go to that version and do stuff that's still okay, that does not break your code, instead of just upgrade everything and destroy everything. It requires one at least partially successful compile because it works on the cargo lock file and a little bit on the cargo toml file. Cargo toml is the file where you define your dependencies, your external crates, and the cargo log file is the file the compiler generates as soon as you compile it, at least partially for the first time. Just as bookkeeping, I used this version to generate the code. And in the normal case where you succeed with compile, the compilation will then be locked to a state of dependencies that worked at some point on that platform. I had to learn the hard way that Mac OS X is not your friend when you compile OpenSSL related stuff. Really not your friend. I gave up. I work on Linux again. So the other one is cargo 3, generates ASCII art, also requires the cargo log file.
What?
Your dependencies.
Of the dependencies,
Okay.
just dependencies, sorry. Yeah, it makes ASCII art, yeah, it's a little short. Really handy if you're wondering why the hell you're including some crate. You can just print crate. Oh, thank you very much. Not much there. Also doesn't compile on macOS because it requires curl and OpenSSL. Really bad. Then we have cargo update. If you have used cargo, you can use several default commands like build, test, doc, and update. Standard cargo update will update your dependencies. The extension cargo-update will add a subcommand called cargo install -update, which will update every binary you installed with cargo install. Yes?
I think it's worth pointing out that cargo functions both as the package manager for your project, and with install you can also install binaries
Yes.
which are independent of your project.
Yeah, like pip or npm, installing binaries into your local system, but fast. And cool, and it works. It's really nice. And yeah, this usually is, yeah, that's what I wanted to say. Updates programs installed with cargo install. Cargo install is the command he mentioned. Cool, and last but not least, Rust FMT format. It's a little too silent for my taste sometimes, because when you just execute it, it will just grab all your source files and just do it. It will just standardize them. There's a standardized form for Rust code. So I would recommend it if you have an indentation war going on inside the project. Just install Rust format and be done with it. It's the easy solution for many of these problems.
Actually, the style is currently being finished, or is it finished already?
No,
Because
it's
there's like an RFC repo for the style Rust format uses. So kind of the standard style for Rust.
yeah. You can also
Discuss everything there.
sure if you want to change the standard, you can do the RFCs.
Currently, there is no real standard, so.
Yeah, it's standard by implementation. But it's also worth pointing out Rust format has a config file which you can place inside your project, where you can define per project. In this project, I would like to have the indentation with 2 spaces, or with tabs, or with 4, or 7.5, whatever. Cool. So there we are. Any questions, comments? So we are done for tonight. Yes, please come to RustFest if you have the time. And hang around. Thank you.